this is the third video for the chapter Refraction, and just to start this off, I'm going to tell you what is the principle of reversibility of light. So for that I'm going to draw the same glass slab and air diagram. You'll be seeing this a lot. Air and glass here. Air on all four sides, but I'm just writing it here. Let's draw the normal a bit more on this side. Here's your incident ray. It's going to bend towards the normal and then back away from it, considering that this is air and over here. So you can see here that the ray is coming like this, bending towards the normal and going out. Now, what this principle of reversibility says is that if you reverse all these arrows here, if your light actually enters from here, it'll trace that same path and it'll come out from here. It'll trace the exact same path. There's a whole detailed derivation and explanation given in your textbook. I suggest you look through that. I'm not going to be doing the whole thing. But the main concept is that if you have a certain ray, it gets refracted, it emerges, and you send it back the same way. If your emergent ray over here, I'm writing ER, emergent ray, becomes your incident ray, then your incident ray on this side becomes your emergent ray. So that's basically what it is. And from that you can also say that mu of medium 2 with respect to 1 is equal to 1 upon mu 1 over here and 2 here. So medium 1 with respect to 2. And again, this is all the explanation is given in your textbook. I'm not going to be doing it, but just know this formula for now. There's nothing tough in it at all. So the next concept, I'll clear this up before moving on. It's called lateral displacement. And as far as I remember, in class 10 we also had to do a lab experiment on it. So I guess you guys would have done it, or we'll do it at the end of the year. So here we have another glass block. Normal is here, or let's again draw it on the side. Incident ray is in blue, gets refracted inside and comes out like this. Now, whether your incident ray is at this angle of incidence here or whether it's coming like this, you'll see one thing that is in common. Your emergent ray here, this is your emergent ray, will be parallel to the incident ray. If I just extend this incident ray here, you'll see it. This is what it looks like, and you can see that I've drawn them to be roughly parallel. And you'll always see this, whether your angle of incidence is very low or very high. It's very high in this case. It'll still turn out to be like this. And when you do this, when you draw this diagram, the distance, the perpendicular distance between these two parallel lines, the emergent ray and what should have been the incident ray had the block not been there, the distance between these two is called lateral displacement. Very important term, and as I said, you'll be doing a few experiments on this as well. Lateral displacement. Why is it called that? Simple reason. Your ray is originally coming here. It should have landed up at this red spot over here, but instead, because of refraction, because of the presence of the glass slab in the middle, it gets deviated and it lands up at this spot here. So gets displaced laterally. Laterally because if you see, you're just taking the ray over here and just shifting it. Sorry, the other way around. You're actually taking what should have been the ray over here and just shifting it downwards so that it comes here. That's why it's lateral displacement. And the distance, the lateral displacement, it depends on a few factors which are again given in a book. You could go through them, but it largely depends on the angle of incidence and also the thickness of the glass block. Why does it depend on thickness of the glass block? That's a simple reason. I'm going to draw a very thin one here. Okay, normal is here. Say your angle of incidence, I'll try and make it nearly 45. It should come something like this. And if I take a thicker one now on the side, I should extend this to show lateral displacement here. And now same thing, 45, nearly 45, I'm not measuring or anything. Something like this. And again extend this. So what's happening is that the distance that this refracted ray, which is inside the glass block, the distance is increasing when you take a thicker block. And this is actually the ray when your incident, refracted, and emergent ray go away from what should have been the incident ray. So the further this ray here, I'll take a different color. The further that this ray here that is traveling inside the glass block, the further it travels, the more will be the lateral displacement, because the more it moves away from the rays here on the side. So those are two factors. And again, if you have a block and you have a ray that is incident like this, it's a perpendicular over here, so it's called normal incidence, where your angle of incidence is 0, so angle of refraction is 0, so lateral displacement is also 0. So that's all there is for all these glass blocks. And now I'll move on to the second part of the chapter, which is again extremely important, and that is all to do with prisms. So in this tutorial I don't have too much time, but I'm going to tell you the basics of prisms, and then in the next tutorial I'll cover it in more detail. So a prism is an object which looks something like this. I'm sure you would have seen it in the lab, or you probably have one at home or something. So you have, how should I draw this? Something like this. It's a 3D thing, so I'm not too good at drawing, but I think that's how it should look like. So it's just a portion of a transparent refracting medium which is bound by three rectangular faces. You can see that there's one on this side, one over here, and one at the bottom. Three rectangular faces and two triangular faces. So there's one here and one at the back. I think if you've seen a prism, you'd be able to visualize this better. So you could go on the net and search for images of it, or I'm pretty sure your lab also has a few. So this angle here, which I've marked in red, this is the angle which is called angle of prism. It's denoted by A. It just tells you that how much is the angle between the two rectangular surfaces on the sides, and that in turn will determine a lot of things later on, you'll see. But just a few more terms. When you place your prism like this, the bottom surface is called the base. These two rectangular faces on the side are called the refracting surfaces. I'll write RS, RS over here, RS over here. Angle of prism, I've told you, and on top, this line that is going on top, is called your refracting edge. So I'm out of time now, but in the next video I'll be drawing a few diagrams of prisms and tell you about the angular deviation on it, and then also move on to real band depth, critical angle, total internal reflection, and I think that should all be done either in the next tutorial or I'll take one more after that. But that's it for this one.